In this video, we are going to talk about differentials. All right, so we've seen for a function of two variables, f of x comma y, that the change in the function, change in f, is approximately equal to the partial derivative of f with respect to x times a change in the x direction plus the partial derivative of f with respect to y times a change in the y direction, change in y. So notationally, there's a way for us to express what I'm going to call sort of like the instantaneous version of this. Okay, so when we talk about the instantaneous version, I'm going to replace this delta f with a df. And this is a notational thing. And when I talk about the instantaneous version, the approximation will change into an equal sign. And I'll get partial derivative f with respect to x. We change the delta x to a dx. Notice it's dx, not del x. I only write that del when I talk about these partial derivatives. So this partial derivative, this is a del f, del y. And then the delta y changes to a dy. Okay, and this is called the total differential. Sometimes I'll just call it the differential. The total differential of f. And we can write down something similar for a function of three variables. So if I had a function g of x comma y comma z, we could write dg is going to be equal to the partial of g with respect to x times dx plus the partial of g with respect to y times dy, and then plus the partial of g with respect to z times dz. So when we write this d, whatever our function is, this is just a notational thing. This is a notational thing. And then what's written on the right-hand side is how we compute it. This is how to compute. So let's look at an example. So in the example, you build a cylindrical can. The radius is about 5 centimeters, and height is about 8 centimeters. And I say about because maybe they're not exactly those values. It says that there's a possible error in both of at most 0.1 centimeters. So this is a real-world scenario. Sometimes when we build things, there might be a margin of error in our construction. And I want to approximate the possible error that would result in the volume. Okay, so the way I do this is first, because it's talking about volume, I should write an equation for the volume. So the volume of a cylindrical can like this is pi r squared times h. Okay, so it's like I have a function. It's like I have a function of r and h. So now I'm going to use my notation for differentials. All right, dv would be equal to, so my function, maybe it's a little bit better to call this v of r comma h, which is just v for volume. All right, so dv, using my differential notation, is equal to del v over del r, so the partial derivative with respect to r, times dr, plus the partial with respect to h, del v, del h, times dh. All right, so now if I start to evaluate some of this stuff, dv is equal to, the partial derivative of v with respect to r is going to be 2 pi rh. So multiply that by dr, plus the partial derivative of v with respect to h is going to be pi r squared, and then multiply that by dh. So del v sort of represents kind of the instantaneous change in volume here. Okay. So we are going to end up approximating that because we don't quite have an instantaneous change in the radius or the instantaneous change in the height. We have more like an interval for how much this change in r and this change in h could be. Okay, so I'm going to say that we are going to sort of approximate this change in volume. Okay, and now we're going to start to plug in values for what stuff is. So we'll get 2 pi r. So my radius is, it's about 5 centimeters, times h, which is about 8 centimeters. And now for dr, I'm going to plug in what delta r would be. And that could be plus or minus 0.1 centimeters. And now the next term, I got plus pi r squared. So r is about, it was about 5 centimeters. So 5 centimeters squared. And then dh, we're going to approximate that with delta h. So the change in height might be plus or minus 0.1 centimeters, sort of at the extremes. It doesn't have to be exactly 0.1 or negative 0.1. It could be somewhere in between them. But sort of at the extremes, it's going to be those values. Okay, so simplifying this, we get that this is going to be equal to plus or minus 8 pi centimeters cubed. That's what the first term will be. Now the next term is going to be plus or minus 2.5 pi centimeters cubed. So overall, we could get, actually at this point I can go and just start to write it. My approximate maximum error is between, actually let's just write it all in one line. The approximate maximum error is between, on one end, if both of these values were negative, I'd get negative 10.5 pi centimeters cubed, which is about negative 33 centimeters cubed. And on the flip side, if both of those were positive on the other end of the spectrum, I could get something as large as positive 10.5 pi centimeters cubed. So this is going to be approximately equal to positive 33 centimeters cubed. So that's what my possible error could be. It's something in between negative 33 cubic centimeters and positive 33 cubic centimeters. The volume of my can might be 33 cubic centimeters smaller than what I intended at sort of the worst, or 33 cubic centimeters greater than what I intended. That's the interpretation of this. All right, so in terms of our goals, we've now completed our final goal for this section, which is how do we use differentials to perform error analysis?